So, welcome to Causal Inference for Survival Data with Time Varying Confounders, Structural Nested Models, and G-Estimation. I'm Lamar Hunt.
I'm Yuchen Yang. This is a project for
Advanced Statistical Inference
Statistical Inference
at Johns Hopkins, taught by Dan Sharfstein.
Yeah.
So this is just an outline of what we're going to talk about. So we're going to go over causal models in general, because I think that'll be helpful for understanding structural survival models. The Rubin causal model, identification, and then we'll get into the meat of the talk, which is structural survival models in general. We have to do a little notation, time-varying confounding, assumptions, and methods to deal with time-varying confounding. And then one of those methods is structural nested accelerated failure time models using G-estimation. So we'll go over what that is and how to deal with two types of censoring.
Yeah, right.
So first we'll talk about the Rubin causal model. So let yi be patient i's observed survival time, xi equal 1 indicate treatment, and xi equals 0 indicate control, and assume that yi, xi, I going from 1 to n are IID. So a causal effect of treatment is one that compares outcomes had, contrary to fact, everyone been placed on treatment to outcomes had, contrary to fact, everyone been placed on control. So in the Rubin causal model, to get something like this, we utilize counterfactual outcomes to model a causal effect. So for example, if we let the superscript 1 be your outcome, individual i's outcome under treatment, and 0 be under control, we might ask what's the expected value for individual I, their outcome under the difference between their outcomes. So obviously one of these is observed and one of these can't be observed.
So for each individual, only one outcome could be observed, but under some assumption, we can get this average over the population, that expectation value. Yeah.
So identification. So as we just mentioned, you don't observe everyone's out. Like if you're treated, we don't observe when you're not treated. So how do we identify the causal effect? So certain assumptions allow us to map distributions of counterfactual outcomes to distributions of observed outcomes, making these causal effects identifiable, right? Because the causal effect is going to be some function of a distribution of counterfactual outcomes.
Right.
There are two assumptions that we need. One assumption is no confounding, which another way this is said is exchangeability. X, in other words, your treatment is independent of your counterfactual outcomes. And assumption 2 is consistency. So if subject I is treated with condition A, then we observe the potential outcome y equal to y superscript A. How could this be violated? So if your counterfactual outcome under treatment was different depending on whether someone else was treated, then it's not just depending on treatment; it's depending on treatment for you and for someone else. And models for those things exist, but we're going to assume that that's not happening here.
Okay.
There's also a third assumption called positivity, which I haven't listed here, but which is basically that
you have non-zero probability for observing each outcome.
Yeah.
Or something.
Yeah. With these two assumptions, we may now write, so the expected value of y given x equals 1, so this is just conditioning on people who were treated, minus the expected value of y given x equals 0. So you can see that as something that could be estimable in like a linear regression.
Right.
We can write that this is equal to the expected value of counterfactual y under treatment, given x equals 1, and that's due to assumption 2, consistency. And the same for the second term there, which is expected value of y under no treatment, given x equals 0. And we can remove the conditioning on x by assumption 1.
Yeah.
So we have some sort of function from a parameter of a model of observed things to a parameter of a model of counterfactual things.
Yeah.
So we just have to estimate the observed stuff.
Yeah, the conditional expectation that could be observed.
Yeah. Randomized trials satisfy assumption 1 by definition, right? Because you just use a coin flip to decide whether you're treated, thereby allowing a causal interpretation of the estimate, the simple sort of linear regression estimate or whatever model you're using. You can just get a causal interpretation for free. That's why randomized trials are so good. Unfortunately, we're not dealing with randomized trials, so there may be confounders. So in the presence of a measured confounder Z, we can modify assumption 1. We call this no unmeasured confounding. So X is independent of your counterfactual outcomes conditional on Z. So what this just means is that if you look at all the people with a particular, if you stratify by Z, within those Z values, then it's a coin flip, whether you receive treatment or not. Whereas if you didn't condition on that, if you looked at the marginal, then you Z might be the reason for the effect. If you haven't measured it, you wouldn't know that.
Yeah. So basically, you need to collect enough Z to make sure that maybe the treatment decision made by the physician or some other people is independent of the potential outcome.
Right. Yeah. And you can't test for these assumptions.
Yeah.
So now we can write the expected value of y conditional on x equaling 1 and whatever your z value is, minus the expected value of y conditionally on x equals 0 and whatever your z value is. We can then plug in the counterfactual outcomes because of consistency, and then we can remove the x's because of no unmeasured confounding, because we assume that conditional on z, x isn't informative for your counterfactual outcomes.
Yeah, right. And then if you want to get the average treatment effect, you can average over z.
Yes.
Get the expectation over z. Yeah.
Obviously, in an observational setting, these assumptions can be violated and they're not testable. So researchers have to use discretion.
Yeah.
Now let's move on to structural survival models. Some notation first. So consider a scenario where patient I is treated on multiple occasions. So I'll call them visits across time before survival time T sub I is measured. We have this overbar notation here. So A overbar sub I. This denotes the sequence of indicators for whether or not the treatment was received on each occasion. M going from 1 to K of I. K of I is basically
number of visits?
Yeah, the last visit for subject I, and it changes from subject to subject, obviously.
Yeah.
So we'll call this a patient I's treatment regimen. So the overbar just means the future from a certain point on, and if you don't have any, if you just have the overbar, it's the whole future from the very beginning. So it's the whole regimen. And the same thing with L. So these are, let's let L overbar I denote a sequence of vectors of potential confounders of the relationship between A overbar I, your treatment regimen, and outcome TI. And this may vary from visit to visit. And let U of M denote the time from treatment initiation to the beginning of visit M. We use superscripts to indicate potential outcomes under a given treatment regime, little a overbar. So T sub I little a overbar is basically telling us subject I's potential outcome when they're treated with the regime little a overbar, which is some particular treatment regime.
So the a overbar always started from time 0?
Yes.
Right? Okay.
If it had a overbar maybe with like a 4, then it would be the future from visit 4 and beyond.
Okay.
I'm sorry, this is the past, not the future. The past from 4 and the future would be an underbar, but we don't.
So overbar is the past. Like if a overbar 4 is the past from 0 to 4.
Yeah.
Okay.
Yeah. So from visit 4 and then all the way into the past. Yeah.
Okay.
This allows us to talk about time varying confounding to make this more concrete, let's give an example. So let L sub M be CD4 cell count at visit M. And let A sub M indicate antiretroviral treatment was received at visit M. So if it's 1, it was received. If it was 0, it was not. And so we're interested in, say, time to AIDS in a patient who has HIV. So we want to know what's the causal effect of continuous antiretroviral treatment versus continuous non-treatment on time to AIDS. So that would be, we want to compare A over bar with all 1s versus A over bar with all 0s. So you can see here that these are going to define counterfactual outcomes because no one is going to, maybe some people might get continuous treatment, but not everyone will. And so we'll have to construct what they would look like had they received treatment continuously versus not.
So it's kind of like, because the treatment is over time, it has like more dimension than a single treatment. So that's why make the problem more complicated.
Yes.
And also we are interested in estimating this kind of like marginal effect. We're not interested in treatment or not at single visit. We're interested in the whole trajectory of whether treated or not.
Like a joint effect.
Yeah, a joint effect of the treatment.
Yeah, and that's gonna cause problems.
Yeah. We'll see why is that.
So, well, here's the problem. So we have confounding, right? So your CD4 cell count at visit M is going to impact the decision that the doctor makes to treat you. It's also going to impact your time to AIDS, because I believe if you have very low CD4 cell count, then you're closer to AIDS, and that's also why the doctor might treat you. Whereas if you had very high CD4 cell counts, the doctor might say you've had enough, we won't treat you. So we have some sort of confounding here because it's L is impacting your treatment and your outcome. But we also have mediation because your treatment at visit M-1, it impacts T partly by impacting your CD4 cell counts.
I think we have a picture.
Yeah, this will make it more clear.
Yeah.
So this is confounding, so you can see the red arrows indicate what I want you to focus on, which is the LM having some effect on AM, but also having an effect on your treatment, or your outcome, T. But then here's the mediation. So A, M-1, your treatment at time M-1 is impacting T partly through your CD4 cell counts at time M.
Right.
And so this is what you were talking about where...
So if we want to, study the impact of A M-1 on T, then we don't want to control for this, right? Because
correct,
we want to have the effect of this pass to play a role in this. But on the other hand, if we want to study like the impact of AM on T, then we need to control for LM because that's a confounder we need to.
But we don't want to do these specific things.
Yeah,
we want to have a joint.
Yeah, so that's what makes things difficult.
So can we build a Cox model, assume no unmeasured confounding, because we've let's say that L captures everything, control for L, and arrive at a causal interpretation like we did before? So what would that look like? So we would have the hazard at time T as it depends on your past at T and your past treatment history and your past covariate history. It's some baseline hazard times e to the beta 1 times some function of the past plus beta 2 times some function of the past covariates. And then maybe look at beta 1 and get some sort of joint effect. Some problems here is like, what is that function? But also, as we mentioned before, you can't really just control for L.
Yeah. You're blocking all the impact
Yeah.
from that mediation path.
Yeah.
Basically, yeah. But I think in some Cox model with time varying covariates, they just assume that given the past, the hazard is only dependent on the current. It's like it's not the whole history, but the current.
Yeah. So you'd use like the very previous.
Yeah. but
Yeah.
it's kind of like an independent assumption
Yeah.
or something.
Okay.
Yeah, it's still a strong assumption.
So as we said, this is going to block mediation. So hiding some of the causal effect of continuous treatment within beta hat 2.
Mm-hmm.
So we have a catch-22, right? Because if we control, we block mediation, but if we don't control, we have confounding. So this situation arises whenever you have a time-varying confounder.
Mm-hmm.
So let's define that formally. So formally, we say that L bar is a time-varying confounder when it impacts your outcome. The ith L impacts all future treatments, and it is also impacted by previous treatments.
Mm-hmm.
So if you look carefully, the situation that we described with CD4 cell counts has that problem.
Yeah.
CD4 cell count is this way.
Yeah.
So in order to deal with it, we need to assume something more complicated than no unmeasured confounding. Because, I mean, let's say that CD4 cell counts is the only thing that matters.
Mm-hmm.
Everything else doesn't matter. So we still have a problem, right? So it's not enough to have no unmeasured confounding.
Mm-hmm.
So we must need something more.
Mm-hmm.
So we call that sequential randomization. So let's talk about that. So we're not going to develop the mathematical details of identification here, but we will state the assumptions for the causal parameter to be identifiable. So we will need consistency as before. If subject I is treated with regime little a over bar, then we observe that potential outcome. And we also need this thing called sequential ignorability. So this is kind of a mouthful here. So we're going to say that the mth treatment is independent of your potential outcome under some regime, given your current covariate value and the past treatment history. So in other words, I know someone's treatment history up until a certain point, and I know what their CD4 cell counts is, from the beginning all the way until now. Whether they get treated next is a coin flip.
Yeah.
Given their CD4 cell counts. So within a certain strata of CD4 cell counts, it's a coin flip.
Right. I think this assumption makes sense. Like if a physician only decide their treatment on, let's say, your current test of CD4 cell count, then I think the treatment is only depends on the current value of your covariates. So I think that's makes sense. That could hold like in real world application, right?
Okay. So in English, given treatment and covariate history at occasion M, treatment at occasion M does not depend on what your potential outcome is going to be under any given regime. So this is just a more general version of no unmeasured confounding. With those assumptions, we're able to actually identify the causal effect that we were interested in, which was basically continuous treatment versus continuous non-treatment. But there are different methods for doing this. So there are 3 methods for estimating the causal effect of a treatment regime in the presence of time-varying confounding. First, there's the parametric G formula, which Robbins came up with in 1986. There's the inverse probability of treatment weighting. And you can see these sources if you want to know more about them. This is Robbins, Hernan, and Brumbach, 2000. And then the one we're talking about today is G estimation. So this comes from Robbins, 1992. We'll put the citation below the video. So now let's talk about structural nested accelerated failure time models. So, I don't know much about
it.
Yeah.
Yeah. So let's say we have our outcome of interest is the survival time, and we want to say study, let's say, the treatment effect on the survival time. So basically, in traditional survival analysis, we have 2 options. One is we fit the Cox model, and another is accelerated failure time model. So the accelerated failure time model basically assume that the log of your survival time equals to a linear function of your covariate plus an error term. And this error term has expectation 0 and have no parametric form.
So this is a semi-parametric model.
Yeah, it's a semi-parametric model. We can translate this to a more like a causal framework. If we take exponential on both sides, and we can write this as this form. This ti0 is exponential of the epsilon term. That is equivalent in our causal framework, the counterfactual thing, because the epsilon term here is unobserved, and our counterfactual for non-treatment is also unobserved.
So that means that this counterfactual under no treatment, or we're modeling, we're not giving a full parametric model.
We're not willing to assume a parametric model on this. So basically, I think the G estimation is also like a semi-parametric thing. Yeah, but we have the parameter of interest. That's our beta. That's the treatment effect.
Mm-hmm.
So here we can think of this X or covariate as treatment, and T as the observed survival time, and T0 is the unobserved counterfactual survival time under no treatment. And this accelerated failure time model state that the treatment accelerate the failure time by e to the minus beta.
Okay.
By this quantity, basically. Yeah. And if we have time-dependent covariate, and in this case we have the time-dependent, like time-varying treatment. So our setting will be like we have a survival time t and our time-varying covariate a over bar t. That's the whole kind of past before the time you die. And BID observations and the AFT model with time-dependent covariate will become this form. So if we compare this form of this, we can think of this as if we discretize this TI, although it's a multiplication, we can think of as TI summation of TI terms.
Mm-hmm.
And more generally, in continuous case, we can make that summation of TI unit, make it to an integral of TI length. So basically, it's just a continuous extension of this formula.
So here we're modeling the counterfactual under no treatment. Mm-hmm. So we're sort of taking your observed, if we go back here, mm-hmm. we're taking your observed TI, mm-hmm. and we are computing from that mm-hmm. your counterfactual under no treatment whatsoever. And so we're sort of, from each time window, there's a sort of impact of treatment within that time window, uh-huh. and we're trying to remove that.
Yeah, we're integrating throughout the whole time you survived. So that is the counterfactual time here. Yeah. Here we can think of this T0 over bar as the observed counterfactual survival time under no treatment throughout. And the treatment AT accelerate the failure time according to this relationship. More specifically, we want to have an interpretation of this parameter psi 0. This is a parameter we are interested in. This is the overall treatment effect in the population. That's if the survival time when you treat it throughout divided by the survival time when you are not treated throughout. That is the joint effect we are interested in.
So to compute this,
mm-hmm.
you'd have all the AIs of t's be 1,
mm-hmm.
and so then you just have an integral from 0 to t sub I, but that's when you're treated the entire. So that would be like t superscript 1 over bar.
Uh-huh.
That would be in the integral. And if you actually compute that integral,
because we have 1 for AI like a constant,
mm-hmm.
so this t1 over bar should be like e psi 0 times t.
Right. Okay.
Yeah, and divided by if this is 0 throughout, this is 1 constant, and so this becomes t, so the t cancel out. So this is this quantity, I think.
Okay.
Yeah. This model models the treatment effect, the impact of treatment on the survival time, but also we have to deal with the time varying confounder L, our covariate. So that's why we use G estimation to adjust for this time varying confounder. In G estimation, we actually assume a model for our treatment given the past treatment history and the past covariate history. What's the probability you are being treated right now? We are putting a model on this. And assume we have this correct model, because we have the no unmeasured confounding, so we can write.
Well, we have sequential randomization, right?
Yeah, that's a generalized version
Yeah,
of no unmeasured confounding. Yeah, so basically it's a kind of give you some independent conditions on that. So now we can write, because your counterfactual here I denote as h psi 0, because in this this is a counterfactual. If you have the true parameter value of psi 0, and so this quantity will become your true counterfactual.
Right.
Yeah, but if this is not the true parameter, then this is something you don't know what it is. So if you have the true counterfactual, the true counterfactual is independent of your current treatment given your past. That is what this statement is saying. Basically, it's just independent, where the psi 0 is the true value.
So F is just like the distribution of treatment at time m. It's independent of your true counterfactual given the stuff that we've conditioned on here. And so under the assumption that psi naught is the truth, we may remove hi of psi naught.
Yeah, right. That's the idea behind G estimation. So the idea is to research over all possible values of psi to find the value psi that make the above statement true.
I see.
So this kind of like not a classical estimation procedure, like you get MLE or something, but here it's kind of like...
It's like a semi-parametric...
Yeah. It's a little bit weird, but it turns out this, I think it's a doubly robust.
So yeah, I guess because we have to model A, but then we also have to model
the T.
Yeah, we're also modeling H psi.
Yeah,
and one of those models can be wrong.
Yeah, and this estimating procedure is still valid.
Okay.
Yeah, I think so. So the model we put on our current treatment given our past is basically just a logistic regression, because we have a binary outcome, treated or not. So for simplicity, we just assume that the probability of treated right now, given your past, is related with your current covariate and your last treatment and some intercept term.
And so this model can be chosen by the researcher. I mean, it can be wrong.
Yeah.
Assuming the other model's right.
Yeah. I think that you can choose the model that you think that is most likely to be correct.
However you think treatment is being determined.
Yeah.
If you think it depends on the last, if you think the doctor's looking at the last two,
maybe
the doctor thinks like he was treated last, so I'm going to continue to treat. So you only include the last treatment.
But the good thing about doubly robust is it allows you to make more mistakes.
Yeah.
Like if this is not true, but you have that like H psi, the model for H psi is true, then you will be fine. Yeah. So in other words, for the case visit, the probability of receiving treatment given the past is only a function of the last treatment and your current covariate value.
Okay.
And how we perform the estimation, we actually fit a logistic regression model given past treatment and the history of covariate and our H psi. And we found the H psi that makes the coefficient.
So we can compute 0. H of psi. So if we go back...
This is fully observed. The TI and AI are fully observed. So you plug in any psi you want, you can have a value for this.
And it may not be the right value.
Yeah.
But if it is the right value, then...
Yeah, if it's right, then this holds. So...
So if it's...
this holds. So So we have this one.
So in this logistic regression, if psi is the true value, your h of psi shouldn't be impacting the probability of treatment after you've conditioned on all that other stuff.
Yeah.
Because
right.
of sequential randomization.
Yeah,
And so, in other words, we want to find the value of psi that makes theta hat 3 in this model equal to 0.
Yeah. That's basically how you perform the independence, like in this regression setting. Yeah. Okay. So that's the ideal case if we don't have censoring, and we could actually observe all the T and all the treatment, and we could do G estimation. We could get our estimate for the treatment effect. But here, because we have like time to event data, so censoring is obviously a very common problem. So we have to deal with that. We have to consider two types of censoring. The first one is the administrative censoring. That means the end of study. So when the study ends, if you are still survived, we don't know your failure time. We just know that your failure time is greater than the current end of the study time. And the second is non-administrative censoring, due to competing risks or some other cause of dropout. That's before the end of study, but the individual just drop out or just loss of follow-up. You don't know. Yeah.
So like if we're looking at time to AIDS, if the person dies of a heart attack, they're no longer in the study, but they didn't reach AIDS either. So they're censored at that time.
Yeah.
But there is a risk. I mean, dying of a heart attack there's risks for that that we may even have data on.
Yeah.
But with end of study, it's simply the study was going to be 10 years, and you enrolled in the 5th year, and your time to AIDS was 7 years. But obviously the study's over by then, so we can't observe you.
Yeah. So those are like two different types of censoring. And actually, in this G estimation setting, we have different techniques to deal with these two types of censoring. So first, to deal with administrative censoring, we replace this H psi with another indicator, delta psi, for whether the subject's counterfactual survival time under both continuous exposure and continuous non-exposure would be censored. So, which means this delta psi, if this delta psi is 1, then the subject is uncensored under treated throughout and non-treated throughout.
And if it's 0, then any one of their counterfactual outcomes would be censored, even if we did observe their actual outcome.
Yeah.
So let's think of an example. So like if let's say you enrolled in the study and at 5 years, and you did reach time to failure after about 3 years, but you were continuously not treated. But let's say that had you been continuously treated the entire way through, you would have reached failure time after 7 years. So we wouldn't have observed you with that administrative sense. So in that case, delta of psi would be 1 for that individual, even though we observed their actual event time.
Yeah, in that case, delta is 0, I think.
I'm sorry, delta is 0,
because you're censored in that counterfactual
it would only be
setting,
1 if, say, someone had entered at 3 years in a 10-year study, let's say, and they were treated continuously throughout, and they reached failure time after 3 years, so before administrative censoring. Had they, contrary to fact, not been treated that entire time, they would have reached failure time, say, earlier.
Yeah.
And so then we would have observed them still.
Yeah.
And so we would have delta of psi being 1 for that person.
Yeah.
And so the idea is we want delta of psi to be 1 for the individuals that we would observe under any counterfactual treatment regimen.
Yeah. I think that's the idea, because the 1 bar and 0 bar is the two extreme case.
Right.
Actually, so you just compute this two extreme case, and if they're both safe, then you're safe.
Right.
Yeah. So that's why we have to discuss whether the treatment is benefit or not. So decide like whether the T1 bar is greater or the T0 bar is greater.
So this is something we just have to assume, right? We're just going to claim that.
Yeah, it's actually in estimation we plug in any psi and we found a psi.
Oh, I see. Right.
Yeah, so we can check this.
Okay,
Yeah,
so this is going to change.
Mm-hmm.
So, okay, so if psi is greater than 0, that means that, strangely, that means that treatment it's harmful.
Mm-hmm.
And so in that case, if treatment is harmful, then if we observe when you have been treated, then we may not observe you when you're not treated because you may have lived longer past the administrative censoring time.
Yeah.
But if treatment was helpful, then if we observed when you were treated, then we certainly would observe when you were not treated.
Yeah.
Because you would only live a shorter amount.
Right. That's the basic idea. But yeah, you can figure out the math.
Yeah.
It's not that difficult, but yeah. Yeah, because this H psi can only be computed for uncensored individuals. But for censored individuals, actually this delta is always 0. And for uncensored individuals, we could compute both of this, and still some of the individual will have a 0 value.
I see. Okay,
Yeah.
so this delta, this is a function of psi that is always, we can always get a value for, whereas H of psi we couldn't before.
Yeah, because H psi we need the Ti, but for censored individual we don't have that Ti.
Okay, it's actually a function of H of psi that we can always compute. And so the idea is going to be that if H of psi is independent of treatment, given the past, then this function of it should also be independent.
Yeah.
Which is computable. Okay.
Yeah, right. Yeah, so we may also have the 0 value for certain uncensored individuals. So thus we created kind of artificial censoring to account for the selection bias. Like we explained before, like if we have administrative censoring, we may just include people like survive under some regime, but not the other. So we have kind of like select people, like have this kind of selection bias. Yeah,
right. So people who would have lived a long time had they been under a different treatment regime, we're observing more of them.
Yeah.
But we should get rid of those people because we wouldn't have observed them had they been
basically
under the other
unbiased sample under any treatment regime we should include. Okay, to deal with the second type of censoring, that's a competing risk.
Well, I guess before we get into that, what do we do now? So we have this delta I of psi. What do we do with it? Do we just use that instead of H of psi in the logistic model?
Yeah, we replace that in the logistic model.
Okay.
Yeah, because
and then
still have the independent.
We find the psis that make the theta 3 again 0.
Yeah, but basically we just easily replace H psi for delta psi. Both of them are computable.
Okay.
Okay, so deal with competing risk, we actually put a model on it because we have, at each visit, people have some probability of being censored by competing risk. So we actually fit another logistic regression to model the probability you're being censored at each time visit. For simplicity, we could just assume that given your history and you're still uncensored at this time, the probability you're censored right now just is a function of your last covariate treatment.
Okay. Yeah. But this could be determined by the researcher.
Yeah. You could pick any other models. We estimate the probability of remaining uncensored until failure time, which means like you remain uncensored throughout until your death, using both the censored and uncensored data. And this probability is the product of probability of being uncensored at each time visit.
So the idea would be we have these indicator variables for each person at each time, whether or not they're censored at that time. And of course, once they're censored, they're continuing.
Mm-hmm.
So it's all ones and then there's a 0 or something.
Yeah.
Or I guess it's all zeros and then it's a 1. Because it's all not censored and then suddenly they're censored.
Oh, yeah. So here 1 is censored.
And so then we use all that data to model the probability that someone's censored, given the things that we do know.
Yeah.
Okay.
And then once we have this parameter, we could fit like for person I at time k, their probability of being censored.
Okay, at time k, but then we need more than just person I at time k. We need person I. What's
Throughout,
their probability that they were censored?
Yeah.
And so probabilities multiply, right? So you just multiply them together.
Yeah, you get the final probability of remaining uncensored at the very last.
So you'd literally multiply together the predictions. Like if you were to do this in R or something, you'd get the model fit values for that person over their time periods, and you'd multiply them all together.
Yeah.
And then that would be the probability of being that end result would be the probability that that person was censored.
Yeah. Yeah. Okay. Yeah. So this, I think it's called inverse probability of censoring weights. So basically, we weight the uncensored individuals by this logistic fit to get the weight, and we weight them in the G estimation.
So when we do our logistic regression, as before, where we're modeling A, the treatment probability, given the L's and the past treatment and everything, we would just do a weighted logistic regression using the weights determined in the way that we just described.
Yeah. So to sum up how we actually perform this G estimation under censoring. So first, we use all our data to model the competing risk censoring to estimate the weight for each individual. And in this step, we treat the administrative censored individuals as uncensored. And second, we delete individuals that are censored by the competing risks. And what we left is only individuals uncensored and administrative censored. And for those individuals, we could compute this delta psi, as we mentioned before. And then we fit a weighted logistic regression. We replace this H psi by this delta psi in the G estimation and do weighted logistic regression with weights for each individual given in the first step.
Okay, so if we have administrative censoring and competing risk censoring, then first we do the model of competing risk censoring.
Yeah.
Because we want to use all that information.
Yeah.
Then we get those weights. Then we remove the people who were censored by a competing risk because they've contributed their information already to the weights.
Yeah.
And then we compute that delta to deal with the administrative censoring, and we use that delta in the logistic regression of the probability of treatment. But then we also just do a weighted logistic regression using the weights.
Yeah, because those censored individuals only compute to the weight, and those uncensored individuals, they represent underlying population by their inverse
I see.
weight.
And then
Yeah, so
if you weight them in that way, then it gives you it's like you're simulating from the underlying population, had there been no censoring at all.
Yeah, right. So because we don't have the censored individual in the final logistic regression, but we still want to represent them.
Right.
And those weights we get by fitting the censored model with all the censored data. That's how we adjust for those bias, I think.
Okay, so this process is described in a paper by Miguel Hernan and others called Structural Accelerated Failure Time Models for Survival Analysis and Studies with Time Varying Treatments. So this is basically, and they actually show the generalized estimating equation that is equivalent to doing this type of a grid search for psi to get the
Yeah.
right psi.
Yeah. Yeah.
So,
So it's actually, I think, basically it's a semi-parametric model,
yeah.
and you could construct the estimating equation
Mhm.
for that model.
Mhm.
But just the model is because of this time varying things,
Uh-huh.
it's described in a non-classical way.
Uh-huh.
So you're not very. I
And-
don't
yeah.
know whether you can get the estimating equation like very intuitively,
So
like in regression setting.
So intuitively, we have dealt with our time varying confounder by using this assumption of sequential randomization. And of course, that's just an assumption that can't be tested. But if you've measured enough covariates, then maybe it can be true. And if it is true, then basically the idea is that you find the psi that makes it true. And that psi is a consistent estimator, a doubly robust consistent estimator for the true causal effect, defined as the ratio of your survival time when you're continuously treated versus when you're continuously not treated.
Right.
Thanks for watching. This has been a discussion of structural nested models and G estimation.
Okay. Bye.